Order statistics. Statistics made to order. All right, so this is going to be a lot of fun. Let x1, x2, up to xn be continuous. We're going to restrict ourselves to the continuous case here. Make it a little easier, actually. Continuous and independent random variables, all with coming from the same distribution. Okay, they all behave the same way and independently. They behave the same way. They're independent, continuous, and they have a common CDF given by this, and their common PDF is given by this. So I'm not going to, denote I'm not going to indicate subscripts put the random variables in the subscripts there because they all we know what their PDFs and CDFs are. Then we'll write like this. If I put x sub k with a k in the subscript but surrounded by parenthesis, this is going to be equal to the kth smallest. It's actually the value of the kth smallest of the xi. Okay? Like, for example, x1 is defined to be with the 1 in parenthesis in the subscript. This is just shorthand notation for the minimum of all the xi's in the set from 1 to n. Okay? And then the maximum, I could also, write just x sub n in parenthesis, like that. This is the maximum overall I, 1 to n, of the xi. Okay? For example, sometimes we're interested in the first and last place finishers in a race. If these are all race times, okay, x1 and x2 up to xn, you've got n people running in a race. You might be interested in the time until the first person finishes. That would be this. Okay. Similarly, this would be the time that you have to wait until the last person crosses the line. Okay, so these random variables are these are functions of the set of these random variables. Okay, and so these functionals here, these of course are not independent, because you should note right away that obviously you're always going to have that the minimum of those is always going to be less or equal to the second smallest, which would be less or equal to the third smallest, etc., etc., and on and on. Okay, so these are not independent. In fact, so if I'm given that the minimum is at or above a certain value, then I know that the next one has to be at least that much. Okay, so let's talk about the distribution of these so-called order statistics, or statistics made to order. First off, I can get expressions pretty easily for the CDFs and PDFs for the first and last ones. Let's start with that. That is, maybe we'll take a look at the CDF for the maximum. Now here I am going to stipulate that I'm looking at the CDF for the maximum for the largest order statistic. Okay, because this quantity, this CDF, is not the same as this F. This F describes the behavior of each one of these independent random variables. This one is, here we're looking at, say, the cumulative distribution function for, say, the maximum race time, the time until the last person finishes. Now, by definition, then, this is just the probability that the maximum is less or equal to little x, right? And now here's how you can get at this. Note that the maximum of those x's is less or equal to little x if and only if all those x random variables are less or equal to little x. Okay, that's a really great observation to make. Okay, here's little x, I guess. x1 is here, x2 is here, x3 is here, x4 is here, x5 is there. Okay, in this example, I guess looks like so here's x1 in parenthesis, here's x2 in parenthesis, here's x3 in parenthesis, here's x4 in parenthesis, and here's x5 in parenthesis. Happens to be the same as x5 and x, you know what I mean. All of these guys are less or equal to little x if and only if the maximum of those is less or equal to little x. They're the same event. So two events that are the same have to have the same probability, right? Okay, so this is just going to be equal to, actually, you know what? All these xi's are independent, right? So this is by independence. By independence, I can write this as the product of the probabilities, right? The product of the CDFs, effectively. And because they're all identically distributed, I got an extra L in there. Nope. It's okay. Because these things all have the same distribution, I can just write that as the CDF for any one of them. Actually, so we just use F, right? But raised to the nth power. Okay. Then we can also get the probability density function for the maximum, right? Because the probability density function for the maximum of those is, we know that this is just, it's the derivative with respect to x of the CDF of the maximum. And so now I'm just going to substitute in there my expression for the CDF of the maximum. It's just the common CDF raised to the nth power. Okay, so how do I take the derivative of all this stuff? It's going to be n times f of x raised to the n minus 1, but then I've got to come back and differentiate the inside. The inside is just the PDF of, it's the common PDF, right? Good. What about the CDF for the minimum? Okay, so this is like, you know, basically we want to know something about the behavior of the time that it takes the first person to cross the finish line, right? So this is the probability that that the minimum of all those xi's, 1 to n, right, is less or equal to little x, right? So here I'm going to play a little trick on this and use the rule for complements. This is 1 minus the chance that the minimum of all those x sub i's. Oh, why are we doing this? Why are we using all this cumbersome notation? Let's just, one of these days I'll get it right, right? 1 minus the probability. Now the minimum of those we can denote like this. It's 1 minus the chance that the minimum is greater than x, right? Okay, now I'm going to take a look at this event here and note that the minimum of a bunch of random variables exceeds x if and only if all of those random variables hit at values larger than x. So this is sort of similar to the trick we played up there, okay, except that now we're going to the other side, right? We've gone to the other side. This is so this is 1 minus. Let's see, what's the chance that that all of those, all the xi's are greater than x. You would say it like that. Okay. And so what is that? That's 1 minus, you know, and again by independence, and they all have the same distribution. It's just going to be 1 minus the common CDF raised to the nth power. Okay. Skipped a couple of steps there, but this is again by independence, and because all those x's have the same, all the xi have the same distribution. Okay, so we can also get the probability density function for the minimum. Okay, right? This is just simply going to be the derivative with respect to x of the CDF. Okay, so I'm just going to substitute in my expression for the CDF there. That's 1 minus f of x raised to the nth power. Okay, so the derivative of 1 is 0, okay, right? If I differentiate this stuff, then I get negative n times 1 minus f of x raised to the n minus 1. Now I got to come in and differentiate the inside there. It's going to be negative f of x, little f of x, the common density function, right? So this is just n times 1 minus the CDF, the common CDF raised to the n minus 1 times the common density function, right? Good.